So we just saw what machine learning is and what are the different types of learning models out there. Now we want to look at the implementation part, the very exciting bit that you are all waiting for. You're going to run your own machine learning model, the very first machine learning model. At the end of this demonstration session, you will have the full code to yourself. Just open up Google Colab, upload this notebook on there, and you would be able to launch your very first machine learning model. Let's get into it, shall we? All right. This is the notebook I was talking about, and I'll link the whole notebook in the description box below. Today, we are going to be looking at a simple iris dataset, which is an inbuilt dataset available within a specific Python library. We're working on an algorithm called random forest and an optimization technique called grid.cv. We'll also be looking at another dataset, California housing. Iris contains information about a particular flower, and California housing is housing sales data. We'll be looking at different visuals as to how you can construct your confusion matrix, feature importance, and how you predict and compare it with your actual values. Let's remember our biryani analogy. It has your rice and meat or your veggies. Features are the spices that you add, which gives you a lot of flavors. Your model is your whole recipe, and then the algorithm is the cooking technique. Random forest is your cooking technique here. The loss function is basically your taste test, where you check for your salt and how your meat is cooked and everything. And then your optimization technique, where you adjust the spices till it reaches that perfection. So let's get into the code. I've given you the detailed instruction as to how the code works. This script basically does a couple of things. We have a plotting helper functions. These set of functions that you see right here, those are called helper functions to visualize the results that we're going to get from training the model. And we have the iris data set. So iris data set where we have the different measurements of flowers. Based on that, the model will be able to predict or classify the different types of flowers. We would be training a baseline random forest model without any optimization. We're going to tune the model using Research CV. We use different multiple settings. So Research CV automatically does that for you. We're going to show the performance before and after the tuning. And we're going to display some example prediction in form of a table for you to understand it better. The correct prediction will be marked with a tick and the wrong prediction will be marked with an X. Just to give you an overview, the lines which starts with a hashtag right over here are comments. So these sentences will not be compiled, but the lines which are colored, some in purple, some are in white, are your actual lines of code. To start off, we would have to install a couple of packages. Python works with these packages. Each package has its own set of functions, has its own set of modules, which runs in the backend of your actual Python code and gets your code up and running. So to install any specific package, you would just have to uncomment this. So by uncommenting, I mean you just have to remove the hashtag so it becomes colored text. If you want to comment it back, you just do a hashtag again. So it's as simple as that. So when you uncomment it and then run it, these packages are installed. So installation command is pip install, and that is how you install any of your Python packages. So scikit-learn contains your data set, the model you're going to be working with, the grid search, CV, optimization technique, and all of those different functions we just spoke about. Pandas handles your tables for you. The data set you're importing for your model. Pandas opens it, modifies it. If you want to add a new column, it does that for you. Pandas is your 101 Python package, which you should know everything about. So NumPy is used for performing numerical operations. If you want to merge two columns or if you want to add column A to column B, so NumPy is your guy. Now, Matplotlib is another Python package. It is basically used for creating plots, charts, all those beautiful visualizations if you want to visualize your data. Once you've installed it, the next step is to import these packages for your code to kind of use it for the whole process. So importing is as simple as it sounds. It's just import and then just take your package name and give it a naming convention. It's not a hard rule for you to follow. NumPy is always NP and pandas is always PD. You can even do NumPy as P. It's not completely wrong, but it will piss some people off, me included. For starters, NumPy is NP, pandas is PD, and matplotlib is PLT. If you look at the way it is being used, matplotlib is called in this specific line of code. We use PLT, but instead, if you have not renamed it, you must be using matplotlib.pyplot.figure, which makes it complex, right? So instead of using the full package name, we give it a short form, and then while calling that specific package, we call it with its short form. Once you've imported the baseline packages, we would be importing different functions from the package scikit-learn, which, as I have already mentioned, gives you your dataset, functions to split your dataset into training and testing sets, and grid-search-CV, which helps in tuning your hyperparameters, which is optimizing your model. Then we have an ensemble module within scikit-learn, which contains all the different machine learning algorithms out there. Today, we're going to be using random forest classifier to classify the different iris dataset. So again, the final module that we're going to be importing is the metrics module, which has the accuracy score, classification report, confusion matrix. These are your model evaluation tools. You've trained the model and the model is giving you predictions. Is it giving you the right prediction? How do you know? Only by these evaluation methods. Let's take a look at the first helper function. This is how you define a function. So DEF is whichever lines of code starts with it. DEF means it's a function and it would have the logic of what the function must do. For instance, this specific plot confusion matrix plots a heat map of where the model got its predictions, right and wrong. So the CM, which is confusion matrix, it's a 2D array of different counts. So, for example, the class names, that is the different categories in the specific data set, is Setosa, versicolor, and virginica. Sounds like Harry Potter spells, but these are different types of flowers out there. And you also can define a title. You can define how your legend of your chart shows up and how many ticks per class you want and rotate the labels so they fit within the chart. This is the code for that. The next helper function is plotting feature importances. What does feature importance mean? Since we've spoken about features, spices, each of these spices are needed in considerable proportion. You cannot add 5 tablespoons of salt and expect it to be delicious. You have a certain amount of salt that needs to be added based on the quantity you're cooking. Compared to salt, the amount of saffron that you add, it's quite less, right? So similar to that, the different features, the model has its own kind of weight on it. So the simple net might have like around 70% of and could attribute like 70% of the model's prediction, whereas the petal's length could attribute to around 60% of a model's kind of like the model's prediction. So based on all of those things, we identified which is the most important feature. It happens at the back end through methods like correlation. We have the output feature, which is flower name, compared to all of these different features. So which feature contributes more towards the flower name? Obviously, the color and the size and so on. We calculate the scores for each feature and identify the most important one. This comes in handy in dealing with the healthcare data set. Let's assume you have cancer patient to be particular. So let's say they have a particular type of cancer, and then you have different information of the patient. So age, their different habits as to do they smoke, do they drink, do they have a family history of cancer? When they are like start being with cancer, all the different demographic and other categories that you can find out. These are your different features. Based on these characteristics of the patient that you've identified in the table, you will be able to predict if a patient can develop cancer over the period of time or not. Because you have this information of different groups of people who already have cancer and their respective characteristics. In the future, a new random person comes in, and then you gather information about this specific person, like their age, history of cancer, smoking habits, drinking habits, etc. Based on your model, which is already learned from all of these past data, it will be able to predict for this new random person B to kind of know that whether, based on all these characteristics, will develop cancer in the future. By knowing these things, each of these characteristics of the patient adds value to the prediction. Age might be a strong factor towards your cancer prediction, but whether you are a left-hand writer or right-hand writer may not have as much importance. If you have a family history, that would be the highest contributing feature in terms of like prediction. So if you have a family history, you have higher chance that this person might develop cancer. So that is feature importance plays a huge picture, and we understand which parameter or feature impacts your model performance. This function sorts your features by importance. You can visualize this using a bar chart, and the relative importance score is also be going to be on the chart. So a final helper function we see today is the plot versus actual, which is a scatter plot where you have all of your like kind of regression tasks out there. If you're like working with, so this specifically you would use it for your regression task. If you're not going to be using it for this classification example, regression is where you print a specific value. Now, this is the main workflow of how the whole script works. We have imported the essential packages and defined our helper functions. The first step is to load the dataset. So iris equals load iris loads the dataset for you because you've already imported it in your first step. You're labeling X and Y, X being the measurements, Y being the target variable, which is the name of the class. So based on all of these measurements, you're going to predict or classify which type of flower it is. So you're going to be giving all of the measurements in the variable called the feature name iris. Get the feature names from the dataset. And you're going to be giving all of your target names under the variable class names from the target names. The next step is to split it into training and testing sets. We usually use the 80-20 rule. 80% of the whole dataset becomes your training data, and then 20% of your whole dataset become your testing data. So this 20% will not be used in actual training. It will be used in testing. But the testing where you make the biryani and then test was solved. With 80% of the data, the model will be trained. We split the whole data set into four different data frames: X train, X test, Y train, and Y test. The X, where all of your measurements will be to train and test. And your Y, which contains all of your target names, will be split into Y train and Y test. This is how you define what is a test size, like 20% in order to point to. And this random state, every time you run this specific line of code, it gives you the exact 80% in that specific training set and then 20% in the testing set. So it is like the seed value you give so that you can repeat or regenerate the same training testing data set. Now, the third step is we're going to be training a baseline random forest model. What is a random forest model? That is a huge concept. I'll explain it in another video, but just understand that it is the algorithm we spoke about. It's a technique as to which will use it, which will use this specific technique to learn from your training data set and give you the classification or prediction that you want. The function here is called random forest classifier, and we are defining it to a variable called CLF. So CLF dot fit is what the model is trying to fit. This is the specific code that you would care. Fit your model to the X train and Y train that you've just created. Next, whatever predictions you're going to make on the X test is your measurements and Y test is your actual expected result. Once this model has been trained, you're going to be storing all the predictions in a variable called preds. And then in order to make your fully trained model to make a prediction, it is with a specific function called clf.predict. And you'll be doing it on X test. So once the function gets executed, it will give you Y test values. If the predicted Y test values equals to the actual Y test values, that's when we know our model has performed better. Now, the fourth step would be to evaluate the baseline accuracy of this model. We're not using any kind of tuning here. We just use the actual recipe and algorithm and run the model. We identify how many correct predictions have been made and calculate evaluation metrics like precision, recall, F1, which tell you how accurate your model is. And when we're creating a confusion matrix, this confusion matrix will help us visualize how far off is a model or how better off is a model. We'll also be plotting the feature importances, which specific measurement adds the most value to the prediction. The fifth step, this is where we do the optimization. Where we use a particular function called with it tries multiple parameter combinations on its own and all at once. It's all automated. So we define how the parameters needs to be tuned. So n estimator is the number of trees. So by trees, I mean within the random forest model, it's a huge forest with a lot of trees, and each trees will help you arrive at the prediction that you're just looking at. Maximum depth is the maximum depth of each tree. Imagine it to be a huge tree making the decision for you. The more depth the tree has, the more enriched output the tree would give you. Minimum sample split. In each of these trees, there will be a node in which you want to be giving value to how it's being split. So I can understand that all these different parameters are entirely new. That too, for you, for your very first machine learning model, it will be very confusing. But don't worry, I'll be taking layman termed explanations to these parameters in upcoming videos. Stay tuned for that. Once you've defined your parameters, you just call the grid search CV and define all the parameters here. Finally, you get all of your results. So print your grid search CV's score and then your best performing model, its accuracy, the confusion matrix, and everything. So that is the code for all of the things we've just defined to visualize them. We also have a table which visualizes how many predictions the model has done correctly and how many it has done wrong. So this is an optional one. You will not do it every time. For this specific video, let's take a look at how the model has performed. As you can see here, this is your baseline model. The baseline model itself is performed very well. It's like 100% accuracy, which usually never happens. The accuracy could vary between 80 to 90 to 95. You have to test for overfitting, underfitting, which is a topic for another time. This is your classification report. So for three of your classes or three of your different flower types, this is the precision, recall, FN score, and support. All of these are better performing models with 100% accuracy, which in a real world sense will not happen. This is how a confusion matrix will look. Based on accuracy, every rosa has been predicted correctly. And then every versicolor has been also predicted correctly. And then Virginica is also predicted correctly. Your baseline model in itself has been performing very well. You need not do any tuning at all. But in the real world case, it is kind of required. Now, let's take a look at the different importance of features that adds to this module. We have these different features here: petal length, petal width, sepal width, length and width. Petal length and petal have the highest importance. Petal length and sepal width adds a little bit of value, but not as much as your petal length. So this is how you visualize your different features. Just to reiterate our cancer example, imagine this is the age factor, the family history factor, whether you're a left-hand writer or right-hand writer, if your spouse has cancer or not, which is highly irrelevant. So this is how a feature importance is visualized and which feature contributes more to a specific prediction. This specific report looks similar after we fine tune a model or use the grid to optimize a model. This is a classification report. The accuracy is 100% and all of the different metrics are 100%. The classification, the confusion matrix also looks good because the model has predicted everything correctly and the feature importance is the same. In a real world sense, you would ideally get a different result because before tuning, your model would not function better, but after tuning, your model would ideally do better. Now, this is a table we were talking about each of these actual species and each of these different predicted species. The model has predicted all of them correctly. This is a top 10 or the first 10 flower categories that was in that actual table. All of them are right. You built your first machine learning model here, and you're free to use this specific notebook. Try different models. As I mentioned, there are logistic regression, boosting, XBoost. For all of these, I will be posting a video in the upcoming days. So please check that out as soon as it comes out. I recommend you check out something called pipeline and column transformer pre-processing techniques, where you pre-process it a bit before when putting it into your model. And there are different parameter grids for deeper fine tuning, which we will be looking at in the next video. I want you to take this specific script and use your own data set. So, where to find a data set, you ask? There are a lot of different options out there. There is this Kaggle, you have GitHub, you have Hugging Face, where you can find so many data sets. I can create one on your own using ChatGPT. Just mention to ChatGPT that you're going to try out logistic regression or random forest and then test it out with the sample data set. ChatGPT would give that to you in an instant.